Hello and welcome to another lecture from my class, PSYC 440-640. The class that's called Experimental Methods, but is really a class about univariate data analytic techniques from a model comparisons perspective. So lots and lots of regressions and ANOVAs done as regressions, and so on and so on. But hopefully some other interesting information for you too. It is springtime as I'm recording this, and I remember springtime. I used to suffer from allergies quite a lot as a kid, thankfully less so now that I'm an adult. But I think there's a special kind of allergy or sort of sickness or sensitivity that those of us who are in grad school or have been through grad school can appreciate, and that is represented here in this two-part webcomic from phdcomics.com. And as usual, it's humor that I'm sure you can appreciate if you've been to grad school or if you are in grad school right now. So enjoy. Here's another webcomic from a series that I don't think I've highlighted before, SMBC.com, Saturday Morning Breakfast Cereal.com. It's very good. A speaker at a conference or a colloquium says, "We call oxytocin the love hormone because it's associated with feelings of attraction." And an audience member raises her hand and says, but it's associated with other things like aggression and sex and labor induction, autism. So you're just picking something romantic to give it pop appeal, but it could be called a million of other things with equal accuracy. And the speaker defensively responds, well, when you're giving your talk, you can call it whatever you like, but it's associated with love, so I'm calling it the love hormone. A moment of tense reflection, and later on, our conference attendee is now a conference speaker saying, today I'd like to talk about oxytocin, the nipple clamp hormone. So again, SMBC.com, well worth checking out. And topical also because it refers, albeit somewhat obliquely, to the an area of the replicability crisis in psychology that concerns the hormone oxytocin. You may have seen this in the news. It was covered about a year ago, maybe a little bit less than that. Basically, oxytocin is a hormone that is associated, at least it appears to be associated in some research, with feelings of love. And for a very long time, in recent science, was popularized, and people gave talks, and there was I forget the name of the author, but someone did a rather famous TED talk about the so-called love hormone. It just seemed to be like this rather flashy finding that probably many people thought was sort of interesting, or it kind of made sense, this idea that there's this chemical that makes you feel love. Well, the problem with this research is that it was very, very selective, and as kind of illustrated in the previous comic, it ignored the fact that oxytocin is associated with a lot of other facets of feelings and thoughts and behavior. And I'm sure any skilled and trained endocrinologist would have pointed this out, but in psychology and the behavioral sciences, perhaps we're a bit late to get to the important points. And the important point that I want to highlight right now is this idea of family-wise error rate and experiment-wise error rate. So recall that family-wise error rate is the type 1 error rate, the false positive rate, across a set of tests that are all related to one specific hypothesis. So you could imagine if you're a researcher bringing people into your laboratory, dosing some of them with oxytocin, others not, they get some sort of sham dose or placebo dose or whatever. There are a set of tests that you might do to evaluate differences between those two groups. It could be as simple as just one test, like a t-test, or it could be multiple tests if you have multiple different groups or you want to do some clever different contrasts. All of those tests are a family because they relate to your one hypothesis that oxytocin is related to feelings of love or whatever. Now, it's possible if you're bringing people into the laboratory and you're measuring the effects of oxytocin on feelings of love, you're also measuring the effects of oxytocin on other feelings. You're bringing people into a laboratory, you're dosing them with oxytocin or not, and then you're measuring feelings of love, feelings of aggression, feelings of whatever else. Maybe a number of different outcome variables that I'm indicating here as y sub 1, y sub 2, and y sub 3. Now, family-wise error rate is important. I've talked about this a lot, probably too much in previous lectures. The basic point being that if it takes you more than one test to evaluate a hypothesis, you should be mindful of the fact that the likelihood of making at least one type 1 error across however many tests you do, will always be higher than the type 1 error rate for any one test. And it can be quite a lot higher. So there's this possibility, this creeping possibility, that you could find a false positive across a set of tests related to one hypothesis, across a family of tests, that is, related to one hypothesis. Now, I kind of downplayed the whole idea of experiment-wise error rate, but it's not unimportant. Experiment-wise error rate refers to all of the tests related to all of the hypotheses within any one study. It doesn't have to be an experiment, but that's the name. So in our example here, if you had a study you were running where you were measuring multiple outcome variables, love, aggression, hopefulness, calm, I don't know, whatever. You might have hypotheses, you probably would have hypotheses about each of those outcome variables. And it's conceivable that each of those hypotheses would have multiple tests. So there are several families of tests, but there's also kind of an experiment-wise group or study-wise grouping of tests. And you could, of course, compute the experiment-wise or study-wise error rate. And it's possible that if you test a lot of outcome variables, you really can very quickly increase the likelihood of finding at least some difference or some effect somewhere among some of the families of tests that you're doing. And that's not, again, a bad thing, provided that you're aware of it and that you're honest about it. Now, the worst case would be something like a researcher who's doing exploratory research but isn't honest about it. So the researcher doesn't really have any clear hypotheses about, how oxytocin is going to affect love, and how it's going to affect aggression, how it's going to affect calmness, how it's going to affect whatever else. He or she just develops a protocol to administer oxytocin or a placebo dose, and then just measures a bunch of outcome variables, but finds finds an apparently significant effect on one of those outcome variables, and then acts as if, oh, that's the one I really predicted. I wasn't just exploring a large range of potentials, I was really had a firm reason to make that one prediction. That's that kind of post hoc masquerading as a priori problem, and researchers, I think, have a tendency to do this, maybe because once you've found an effect, it's easy to talk yourself into believing that you sort of figured it would happen all along. Relatedly, you can imagine the researcher running a lot of different tests, testing a lot of different hypotheses, oxytocin's relationship to love, oxytocin's relationship to aggression, and so on and so on and so on, but then only reporting in his or her papers or his or her talks the tests or the family of tests that show significant effects, like, oh, well, we found the effect on love. Well, that's cool, potentially, but it could be a type 1 error if you tested a lot of other hypotheses that didn't come out, or even that did come out, but you just chose to kind of ignore or downplay because they weren't as interesting or as easily interpretable to you. This is sometimes called the file drawer effect, because there's this idea that null findings, or even findings which are just difficult to interpret or just, subjectively not that interesting to the researcher, get thrown away in a file drawer, or I suppose nowadays in like a lost computer directory, so, somewhere on your hard drive or on your flash drive, and don't get ever reported. So over time you get a literature which emerges that kind of suggests that there's this effect in one direction, but it ignores all the other failed effects or found effects in other directions. So if that sounds a bit vague, the big criticism nowadays of the oxytocin love research is that it's probably an example of a massive file drawer effect. There were probably lots of other effects of oxytocin that were just kind of unreported or underreported, giving casual readers or casual viewers of that literature the mistaken impression that the oxytocin was kind of relatively specifically and unambiguously associated with love and not a lot else. And that's just not true. And again, I think back to when I was a biology major as an undergrad, and you take like the unit on endocrinology in your bio classes, and you realize that all these hormones are really complicated and how they relate to each other is super complicated, and it makes it seem nowadays to me so sort of naive that we would ever think that, oh yeah, give people oxytocin, it makes them feel love, and that's all there is to it. Anyway, enough sermonizing, I suppose. I just thought this was a kind of an interesting example of a point that's maybe a little bit difficult to grasp. That is the point of experiment-wise or study-wise error rate. And anyway, I wanted to share it with you. And with that out of the way, let's move on and talk a little bit more about ANOVA. Now in today's class, I'm going to go ahead and talk a bit about planned contrasts, and we're going to do some more practice with ANOVA, and I'm going to give you a rundown of some of the assumptions that accompany ANOVA. And these aren't massively different than the assumptions that accompany regression, because of course ANOVA is just a special case of regression. So that part of the lecture hopefully will seem like a bit of a review to you. Okay, let's get going. Now where we left off last time, I kind of made the point in the previous lecture, or the one even previous to that, that when you're running a regression and you have a predictor variable that is categorical in nature and that has especially more than 2 levels, you need some sort of set of coding variables to allow you to handle that predictor variable in your model, in your regression equation. And there are different schemes for doing this coding. The simplest is called dummy coding, and dummy coding, it just occurs when you have sets of coding variables and the values for those variables can only ever be 0 or 1. Now dummy coding schemes or sets are pretty easy to set up, and they work well if there's a particular level or group in your categorical predictor variable that's a natural comparison group or a control group. So if you had a predictor variable which is psychotherapy, and there's like the waitlist group and psychotherapy A and psychotherapy B and like psychotherapy C, so 4 different groups, it makes sense that that waitlist group is like the control group for all the other groups, or the comparison group for all the other groups. Or if you have a study where people in your laboratory do a task under no emotional manipulation, they solve some puzzles or whatever with no apparent emotional tone, and then they do this, or another group of people do the same task under negative emotions, they're given some sort of threatening stimuli, and then a third group of people do it under positive emotions. You could kind of reason that the no emotion condition is like the control group for the other 2 emotions, and thus it makes sense to use it as a natural comparison group or control group. Dummy coding makes that fairly easy, although you can do those same types of comparisons in other coding schemes. Dummy coding has some limitations or some potential downsides. One is it doesn't allow for grouped comparisons, so you can't do contrasts where you combine 2 or more groups and say like, okay, the waitlist group in my psychotherapy example as compared to all psychotherapy combined, and then like psychotherapy A and B combined as compared to psychotherapy C. That type of grouping and comparing you just can't do in dummy coding, which, depending on your goals, might be a problem or might not. Another issue in dummy coding is that all your comparisons, all your contrasts that is, are going to be non-orthogonal in nature. Again, not necessarily a problem, but just something to potentially think about. Another coding scheme I talked about is called contrast coding. Contrast coding is similar, except here our sets of coding variables can be integers. They can be positive or negative whole number values, or they can actually be fractions, and I'll talk about that in a supplemental lecture. These are a little bit harder to set up. There are a couple basic rules or guidelines that you use for setting up contrast codes, and I talked about those last time. We'll review that a little bit today. They do have some nice features though. They allow for grouped comparisons like I described earlier, and those are sometimes useful. Also, depending on how you set up your contrast codes, your contrasts or your comparisons can be either orthogonal or they can be non-orthogonal. It's kind of up to you. So I've said orthogonal and non-orthogonal a couple times now, and I'll acknowledge this is a tricky concept, I think, for people to think about, certainly for me to think about, so much so that I actually made a whole separate supplemental lecture on orthogonality, which I will post very soon. So it's either available now or will soon be available. For the time being though, let's just review that orthogonal contrasts are contrasts that are independent of one another. And one way to think about this is that they compare different chunks of variance, non-overlapping chunks of variance to one another. Non-orthogonal contrasts are not independent. They concern some of the same chunks of variance. There can be overlap in the groups or the chunks of variance that you're comparing in one contrast and the chunks of variance that you're comparing in another contrast. Now, why do we care about that, or what were the consequences of this? Well, To simplify things a little bit, we can just say that in orthogonal contrast, groups of comparisons that are orthogonal to one another, the results are usually simpler to interpret. They're cleaner in the sense that we can often we can feel more comfortable in describing one contrast as, say, being significant and the other one being non-significant because they're entirely discrete and distinct from one another. Another advantage or sometimes nice feature of orthogonal contrast is that there is a limited number of them that you can do. For any particular categorical predictor variable, there is a limit to how many different orthogonal contrasts you can make among the various levels of that predictor variable. And to the extent that we generally want to limit the number of tests we do so as to rein in as much as possible family-wise error rate, that's a good feature, or an attractive feature. Non-orthogonal contrasts can be somewhat more challenging to interpret, especially in factorial designs, that is, designs where we have more than one categorical predictor variable. So far we've only considered situations with one predictor variable, but of course we could have situations or analyses with multiple predictor variables. Anyway, in those cases, it can be a little bit more challenging if our contrasts are non-orthogonal, because now those contrasts are necessarily kind of associated or tied up with each other. So if one's significant and the other isn't significant, and then this interaction is significant and so on, the interpretation is not always as clean as we would like. Although it really depends a lot. Another feature of non-orthogonal contrast is you can do a lot of them. You aren't constrained to the absolute number of them as you are with orthogonal contrast, and to the extent that this can allow you some latitude to do a lot of tests, you can, whether you realize it or not, increase family-wise error rate. So you have to be a bit mindful about that. Again, I have a whole supplemental lecture on this, and we'll talk about non-orthogonal contrast and orthogonal contrast a lot. And it's not that like one is good and the other is bad, but it's worth being at least somewhat familiar with the concepts and how they play out in your analyses. More review, more kind of where we left off last time. You're really the important idea here, or an important idea that I talked about in the previous lectures, is that when we use coding schemes, whether dummy coding or contrast coding, and then we apply those coded variables, or we enter those coded variables into a regression analysis, the regression coefficients that we get are interpretable as either group means or contrasts between group means, and that's often really useful to know, because often we care about contrasts between group means. So here's a screenshot of my Excel spreadsheet for my orthogonal contrasts using the placebo, low-dose, high-dose pharmacology research example. And you can see here that the way I've set up these contrasts, my first contrast is a comparison between the placebo dose group and the low and high dose group combined. So in a sense, that comparison singles out placebo group and compares those two chunks of variance. Which is, from a pharmacologist perspective, might be useful, because it's kind of like testing, is there any effective drug regardless of low or high dose? Because if all that the drug is doing is accomplishing a placebo effect, then there would be no difference between the placebo dose and the low and high dose group. And then the second contrast, which is kind of accomplished by the second coded variable, ignores placebo group, which has already been pulled out, and then compares two chunks of variance, the low and the high dose group. So knowing about those comparisons can be really, really handy, because those are comparisons that we might want to make. That second comparison or that second contrast kind of gets at the dose effect of the drug. Do you need a high dose to get the effect as compared to a low dose, or are the effects of the drug kind of similar across these two somewhat arbitrary dose levels? So you can kind of see this, I hope, visually if you just look at the coding scheme and kind of think about what it represents. But we can also kind of demonstrate this idea algebraically if we plug in values for the coded variables, much as we did with the dummy coding example. It's the same basic idea, except the algebra here is slightly more complicated, although not desperately so. So let's start with the group that gets 0, 0 for the two coded variables x sub 1 and x sub 2. Well, unlike dummy coding, there isn't a group that gets this code. Instead, what this code is referring to is the entire sample. It's a bit like saying, if you had no information about which group a particular person is in, what's your best prediction for that person's value on the outcome variable? And of course, the best prediction, absent any information about their group membership, is the overall sample mean. So we can use that logic here. We can take our basic equation, we can substitute in 0, 0 for x sub 1 and x sub 2, and we can say that the predicted value for that person is the predicted value for all, or the entire sample. And the predicted value for the entire sample is just the mean for the entire sample, and the only term that's left on the other side of the equal sign is b sub 0. So b sub 0, the intercept, is the overall sample mean. And that's just a consequence of the algebra here, but it's worth noting that this is different than how it worked in dummy coding, where in the case of dummy coding, b sub 0 was the mean for whichever group got 0, 0, which is often going to be our comparison group or our control group. So again, b sub 0 is the prediction that the model makes when group membership is not known, which is equal to the grand mean or the overall mean, assuming sample sizes for each of those groups are equal. And if you wanted to, you could represent that as the average of the averages for each of those groups. So we just, the average for the placebo group plus the average for the low dose group plus the average for the high dose group divided by 3. That would just be another way to represent that idea of the overall mean or the grand mean for the sample. Now let's move on to the placebo dose group. Now the placebo dose group in our coding scheme was coded as -2 for x sub 1 and 0 for x sub 2. Let's go ahead and substitute in those values for the terms in our equation here, just as you can see. And the equation simplifies a little bit. And again, we already know b sub 0, so we can substitute in that quotient from the previous slide into the formula as so. So here's where the algebra is going to start to seem a little bit more complicated. We've substituted in the quotient that represents the overall sample mean or the grand mean, and you can see here that we can solve for the regression coefficient b sub 1. And it's not really all that hard. It looks like this. b sub 1 is 1/3 of the difference between the average of the low and high dose group and the placebo dose group. So again, b sub 1, 1/3 of the difference between the average of the two treatment groups and the control group. Now you may be wondering, why 1/3? Well, 1/3 is just because of the way we coded the variables. And in fact, if you look at my supplemental video on coding, you can see that we can get rid of that 1/3 fraction, it's sometimes called a scaling factor, by using fractional codes for our contrast codes. If we use whole number codes, whole integer codes, then we'll almost always end up with these fractional scaling factors, which aren't a big deal. We have to remind ourselves that b sub 1, its absolute value in terms of its the unstandardized regression coefficient is just 1/3 of this contrast that we're interested in. So let's move on and look at the high dose group. The high dose group are the people who get coded 1 for x sub 1 and 1 for x sub 2. So we can go ahead and substitute in those values for x sub 1 and x sub 2 in this equation. And we know that the predicted value for the high dose group is going to be equal to the average for the high dose group. And we've already solved for b sub 0 and b sub 1. So clearly what we're going to try and do here is solve for b sub 2. And there's a bit of algebra here that I'm not going to show you, but it's just a matter of manipulating fractions and moving numbers around, as much of algebra is. And when you get to the very end of it, you find that b sub 2 is equal to half of the difference between the high dose group and the low dose group. And that's good, right? We want b sub 2 to be equal to, or to refer to, the contrast or the comparison of the high dose group and the low dose group. The only thing that's a little bit maybe unexpected is this fractional scaling factor. The fact, referring to the idea that b sub 2, the unstandardized regression coefficient, is equal to half of that contrast. So here's the important points, or some important points. Contrast coding can help us focus on comparisons that we want to make, especially ones that are related to hypotheses we have. So in our example here, it makes sense that we might want to evaluate the differences between these three groups as a set of two contrasts. The first comparing no drug to any amount of drug, and the second contrast comparing a low dose of the drug to a high dose of the drug. Interpreting these coefficients can be a little bit tricky, at least a little bit trickier than when you use dummy coding, because the math is slightly more challenging, although not desperately so. Also, this idea that if you use whole number integers for your contrast code, you end up often with these fractional scaling factors. But if you watch my supplemental video, you'll see there's just a pretty simple way to resolve that, and you don't have to resolve that. You can just multiply when you look at the regression coefficients if you want to know what the difference between those two groups are in your contrast. Anyway, hopefully that seems kind of clear to you. If it doesn't, we can practice in class. And let's right now just consider some different ways to do contrasts with ANOVA type analyses. We'll look at some different ways to do ANOVAs that take advantage of contrasts. And for the purposes of our class, we're using the data set that I'm calling Viagra 3, the SPSS data set. Again, this is based on the original data set from Andy Field's Discovering Statistics Using SPSS. The first thing that we're going to do is try to analyze the regression using our contrast code. So we're going analyze the ANOVA as a regression using contrast codes. So as we've done before, analyze regression linear, our outcome variable is libido, our predictor variables are going to be our two contrast coded variables, the first referring to placebo versus low and high dose group, the second referring to low dose versus high dose group. And if you do that, you get some regression output that looks a little bit like this. Here's your ANOVA, suggesting that the overall omnibus effect is significant. That is, a model which includes group membership, in this case coded using contrast-coded variables, is a significantly better predictor or descriptor of the variance in the outcome variable than is a model which does not include that information. And here are those coefficients from the regression output, where we can see our contrasts between placebo and low and high dose group, and and low dose and high dose group. And if we look at those little t-tests for each contrast, we can see which one is significant. And it's worth noting that these are orthogonal contrasts. By the way, if we wanted to, we could just multiply each of those unstandardized coefficients by their by the number appropriate to their scaling factor. So multiply 0.633 times 3, and that would give us the absolute difference between placebo and low and high dose group, and we can multiply 0.9 by 2, and that would give us the difference between those two groups. You get the same results using Excel if you run a regression analysis. You can kind of see that here. I'm just including this to make the point, as I think I've made before, that it's handy, I think, to try to run the same analyses in Excel and in SPSS just as a way of getting more comfortable with using different types of software to do the same type of analyses, and also checking your work, seeing if you get the same results if you do the same analysis in two different software packages. Now we're going to go ahead and do the same analysis, except we'll use the one-way ANOVA module in SPSS. So here we're going to analyze compare means one-way ANOVA. Remember, one-way ANOVA just refers to an ANOVA with one and only one predictor variable, that predictor variable being a categorical variable, or a factor as it's sometimes called. Our dependent list, as our outcome variable, is just one variable, libido, and our factor, as our predictor variable or our independent variable, is dose. And here we don't need to use a coding variable or a dummy coded variable or contrast coded variable, because the ANOVA module will handle or can handle a categorical predictor variable. What's going to be a little different here is before hitting OK, we're going to click the button for contrasts, and we're going to enter our two contrasts. The first one, we enter those coefficients just typing in 1 and then add, and then 1, then add, and then -2. And then we hit the next button and we do the next contrast, which is going to be 0, -1, and 1. And hopefully these numbers are familiar to you. They're just the same numbers as we used for our contrast codes to compare in the first contrast, placebo group compared to low and high dose group combined, and in the second contrast, low dose group compared to high dose group. So this is maybe one of those examples where if you are familiar with setting up contrast codes so as to run an ANOVA as a regression, it actually is handy, because then if you later on for whatever reason want to just use the ANOVA module, maybe you just want to be quick about it, you can use that same information. And you'll see, hopefully, well, not hopefully, I know how this is going to work, that we'll get the same results. Oops, one last thing. While we're at it, let's ask for some options here. We can ask for some descriptive statistics. We can ask for a means plot. We can ask for a couple other tests, which I don't think I'm going to look at right now, but which we'll consider a little bit later. So anyway, here's our output. We get an ANOVA table for our ANOVA analysis, and of course, the results are the same. The nomenclature or the naming conventions are a little bit different. We've got the naming conventions between groups variance, which is going to give us the same values as what was called regression in the ANOVA table for our regression analysis, and within group variance, which is the same as residual in the ANOVA for our regression analysis, and total, well, that's the same either way. But the numbers are all the same. It's just a different naming convention just based on kind of history and tradition. We also get a little handy table for our contrast coefficients, and this is maybe a place where we can just double check our work and make sure that we got the coding the way we wanted it to. And here we did, because it's pretty simple and we've done this a couple different times, so you could just double check your work. And here is a table for our contrast tests, and we get a test of our first contrast and a test of our second contrast, and it's actually done two different ways. One, assuming that the variances in these groups are the same or are equal, and another assuming that they are unequal. And that actually gets to one of the assumptions of regression and ANOVA that I'm going to talk about a little bit later in this lecture. If you ask for descriptive statistics, you also get a table of descriptive statistics, and if you ask for a means plot, you also get a means plot. The only point I'll make right now is just a subtle warning, or not so subtle warning, I suppose, that SPSS scales its graphs in a way that, to me at least, seems to emphasize differences. So it's more than once has been the time that I've done analyses in SPSS and I'll create a means graph kind of like this, and it'll look like, whoa, there's this big difference between these groups, and then I'll squint at the y-axis and see that SPSS has scaled it in tiny decimal fractions, kind of exaggerating what may be a very small difference. Whether that's a big deal or a small deal to you depends a lot on what you're doing, and of course you can, if you want, double click on the graph in the output screen of SPSS and open up the chart editor, and you can change the scaling on that axis if you wanted to. Here it kind of looks like there's this big difference between the high dose group and the low dose group, but I don't know, like it's what, 1.5 points on a scale. Whatever that scale is, maybe that's a big difference, maybe it's not. Just worth keeping in mind that SPSS will sometimes fiddle with the scale, and you should probably always check your y-axis. Okay, so we've done essentially the same analysis, running the ANOVA as a regression, if you will, and then running the ANOVA as, well, an ANOVA in the ANOVA module. Let's do it a third way. Let's use the GLM module, and here it's going to be a little bit like what we did with the ANOVA module, because we don't have to use coding variables. We don't have to enter contrast coding variables. We can enter dose of Viagra as a fixed factor. Our dependent variable or our outcome variable, of course, is going to be libido. The tricky thing about doing contrasts in GLM is that there are very few options. Now you can see there's a button here, and there are a few kind of pre-made contrasts that you can do. We're going to ignore those for the time being, and just quickly note that you can do contrasts in the GLM module, but you have to use syntax for it. So here is a screenshot of my syntax window where I'm just pointing out different ways that you can do essentially the same contrasts in different parts of SPSS. Now the GLM module is the little bit of code at the bottom there, and it's pretty obvious. You're saying GLM for libido by dose. That's kind of the syntax that we use. It's the outcome variable by the predictor variable, or the dependent variable by the independent variable. The I'm not sure what the official sort of like coding language is here, but the argument that GLM can take is called L matrix. L matrix equals, and then in parentheses you can give it a name. Our first contrast being placebo versus low and high dose group, and then I end my quotes, and then I use the variable dose, and I input those same hopefully familiar values, -2, 1, 1. Then I hit return, and I make another L matrix argument for my next contrast, and then I hit enter, and then I have to make the argument design equals dose. That's just the way it works. Hit a period, and if you run that, you should get some analyses. By the way, there's another command in SPSS syntax called uni-ANOVA for univariate ANOVA that basically works the same way. And there is one way, which is the command associated with the one-way ANOVA module. You would see that if you paste it out from the one-way ANOVA module. And it basically works the same way, except it takes arguments called contrast, which you can see kind of do the same thing as L matrix, but it's a different argument. So again, just to be clear, if you wanted to use syntax and you wanted to do your analysis as a one-way ANOVA, that is using the ANOVA module, you have to use the argument contrast. If you're doing uni-ANOVA or GLM, both of which call or access the GLM module, you use the command, or I'm sorry, the argument L matrix. And at least at this stage, with just one predictor variable and two simple, or relatively simple contrasts, it's hopefully fairly obvious. Anyway, highlight, let's say, the GLM syntax, hit the green triangular run button, and you get some output. Part of your output is the test of between subject effects, and the line we want to pay attention to here is the line for the corrected model. And you can see that the naming again is a little bit different in this module as compared to the previous modules we've worked with, but the numbers are the same. So the so-called type 3 sums of squares and degrees of freedom and mean squares, same, F statistics same, significance level the same. And that's good because we're doing the same analysis, we're just using a slightly different approach in SPSS, so we would hope to get the same results. We also, because we asked for some contrast, we get some tables of contrast results, and you can see our first contrast and our second contrast here, and you can see which one, the first is significant, the second one is maybe marginally significant. The thing to note here is it's basically the same results as we got before. So if we look at the results from our ANOVA analysis, you can see the numbers here for our first and second contrast. Those are the same numbers that you see in our table, our output for our GLM analysis. So maybe this is like a gee whiz moment for you. I know the first time I discovered this, I was like, oh wow, that's so cool. But you know, you can see that it's the same information and same test. Okay, so if you're in my class, and you know, now would be a good time to just sit and think about what you've learned. Does this make sense to you? And in class, I'm going to start doing this exercise where I hand out a note card and ask people to write down something that they don't understand. Because I find that sometimes in class when I say like, hey, is everyone following along? People kind of nod because they want to be polite, or maybe they feel embarrassed to speak out. So if you're in class, I'll be asking you at this moment to write down something. If you're not in class, you're just watching this video on YouTube, you know, take the time anyway and write something down, or write something in the comments field, and as best as I can, I try and read those comments fields, and if I can answer a question, I will. Okay? So think about what you've learned so far. Does this idea of using contrast-coded variables to handle contrasts in one-way ANOVA, and doing it some different ways in regression module, in ANOVA module, in GLM module, does that kind of make sense to you? Hopefully it does. If it doesn't, let's see if we can help it make sense to you. Now, with that in mind, let's go ahead and move on and talk a little bit about the assumptions of ANOVA. And maybe in some ways I should have addressed this early on. I mean, if these assumptions are not met or not adequately met, then maybe it doesn't make sense to do an ANOVA. But I kind of postponed this a bit just because I wanted to really get into ANOVA, and because you'll see, hopefully, that I've covered some of this material already. Basically, the assumptions that we're going to make for ANOVA are the same as those for other general linear models. That is, the same as other regression type analyses, because as I've said repeatedly now, ANOVA is just a special case of regression. So those assumptions are things like our outcome variable is measured on an interval scale. It's a continuous variable. It's not categorical. Our data is independent for our outcome variable. There's a normal sampling distribution for our test statistic, in this case f, and technically it's not a normal distribution, but it's one that is regular and well defined in shape. It's that weird Fisher-Snendikor or whatever it is sampling distribution, which isn't normal, but it's based on the normal distribution. We're also going to assume that there's homoskedasticity, that is homogeneity of variance, and I'll talk about each of these in the following slides. Before I get there, though, I want to address a point that you sometimes see in stats textbooks or in stats classes, and that's the idea that ANOVA is a robust test. So sometimes people say, ANOVA is a robust test, and what they mean is that the results of the test, that the test statistic, the F statistic, will be accurate, will be unbiased, even if there are violations of the assumptions that go along with ANOVA. And to be clear, this is not always the case. When we have violations of assumptions, and this is true for ANOVA, and it's really true for any test statistic calculation we make, there are sort of two fundamental questions to ask. One is, does the test control for inflation of type 1 error rates when there are violations of assumptions, or instead, does it start to give us false positives? And the other side of the coin, if you will, is, does the test have adequate power when there are violations of assumptions, or does it start to potentially miss real effects, give us false negative results? So again, the conventional wisdom is that ANOVA is kind of a robust test, meaning that, yeah, you can have some violations of the assumption of heterogeneity of variance, but it's not a big deal because you're doing an ANOVA, and that's a robust test. Perhaps this is less so the case now, but I can certainly remember back in grad school and undergrad, you take a class on statistics where ANOVA would be covered, and someone, the teacher or the grad student teaching assistant, would say, yes, ANOVA is robust. Now that's not true. Well, it is sort of true when group sizes are equal. That is, when the groups that you have in your sample, like the low dose group, the placebo dose group, the high dose group, all contain the same number of participants or cases. When that's not, when the group sizes are unequal, type 1 error rates, power, and other features of our test statistic can change in weird and unpredictable ways. Let's consider violations of the assumption of homoskedasticity. So in groups comparisons analyses where we're comparing different levels of a categorical predictor variable, we often like to see the variance, that is the variability with respect to the mean for each of our groups, being roughly the same, or I guess ideally exactly the same, but that's often not the case. So in this example here, we've got two different levels of a predictor variable, two groups, and there appears to be a violation of the assumption of homoskedasticity because the one group on the left has got a bunch of outliers in it, and the one on the right doesn't apparently have a bunch of outliers in it. Now, the F statistic that you could make comparing these two groups, or indeed the T statistic you can make if you just did a T-test, would probably work fairly well, would be fairly unbiased, if the two group sizes are pretty much the same, or I guess if they're exactly the same. When group sizes are unequal, if the larger group has the larger variance, then the F statistic tends to get pretty conservative, meaning that the type 1 error rate will get too low, and the power of the test will get too low. The test will tend to have false negatives. It will miss potential effects. If we flip things around, if the larger group has the smaller variance, then the F statistic gets pretty liberal, meaning the type 1 error rate will get too high and the power will get too high. You'll run a greater risk of having results which appear to be real effects but are in fact false positives. Now, if that's a little bit difficult to kind of take on board, that just kind of abstracted set of principles I just offered, let's consider more of a real-world example. And this is something that actually comes up a fair bit in pharmacological research, or indeed other kinds of clinical research. So imagine we're doing some research on a new drug, and we have two groups, a group that gets the drug, a group that gets the placebo, and we're good researchers, so we start out by recruiting a large sample and we assign an equal number of people to each of these two groups, or each of these two levels of our one predictor variable, that is, group assignment. What likely will happen when we go on in our study is that more people will drop out of the active treatment than will drop out of the placebo group or the control group. And that's not always the case, but it just often is the case, because the people in that group are actually getting a drug, which means some of them are going to start to experience side effects, and they might feel sickened or frustrated or just demoralized, and they'll drop out. More so than people in the placebo group who, there are such things as side effects that show up in placebo groups, but those tend to be less common and less extreme, and so folks in that group maybe are willing to hang out. The active group will end up with more variance, and it'll be likely that the distribution of response in that group will be less normal. It will be more variable. That's just the case. Some people will really respond to the drug, some people will not. And again, this is fairly common in treatment research, certainly in pharmacological research. Now imagine we're doing this analysis, we're doing the study, and we run our analyses, and our F statistic reveals significant effects. But the test may have been too liberal because our smaller group had larger variance. We lost people in that active treatment group, but in addition to losing people, the people who remained tended to have a lot of variability in how much they experienced their symptoms, because some of them really responded to the drug, others really didn't. Meanwhile, our placebo group, more people stuck around, but they're all pretty similar to each other because none of them were getting the active drug. So we ended up with a small group with greater variability, a large group with less variability, and we know, and this can be demonstrated using simulations, that F statistics will tend to get a little bit liberal. So we found what looked like a significant effect, and it might be, but it might be a false positive. And if we were to run the test again, recruiting a new sample of people and trying to run the experiment again, we might find that the results don't replicate, and that might be tremendously frustrating to us. I think our heads want to explode. And now that's just because of the way test statistics like the F statistic respond to violations of assumptions. In this case, the violation of the assumption of equivalent or nearly equivalent variability in each of the groups. An important point I guess we can make here is it's good to have equal group sizes. Unequal group sizes make violations of assumptions, in this case violations of the assumption of homogeneity, much worse. So, small samples, as we discussed way back in Unit 1 or Unit 2, small samples make violations of assumptions much worse. In ANOVA type situations where we have different groups, unequal cell sizes or unequal group sizes make violations of assumptions much, much worse. Of course, there are other reasons why we want to have equal group sizes. We can get spurious effects associated with sampling bias. Differential attrition can make it complicated for us to decide whether our groups are really comparable after half of the treatment group dropped out and only a couple of people in the control group dropped out. Maybe these, in a sense, are more kind of like design or methodological considerations. But again, the important idea here is homogeneity of variance. It's an assumption that we often make with ANOVA. It's one that ANOVA is fairly robust to, provided that group sizes are equal. If they are not equal, then it can become really challenging to interpret the results of an ANOVA. So let's consider the assumption of normality. Now remember, we can think about normality in different ways. One way is just to think about the sample data itself, like are the values of the outcome variable normally distributed across the entire sample, or maybe more interestingly, are they normally distributed within each of the groups that make up our entire sample? If we think about this, let's remember that normally distributed data is nice, but it's not absolutely necessary. If our data is normally distributed in each of our groups, especially if there aren't a lot of outliers, then we feel more comfortable saying that the sample statistics that we have, like the mean for a particular group, is probably a pretty good estimator of its parameter, that is the mean for that group in the entire population. Again, this is really if we see sort of normally distributed data and if we see an absence of extreme values, outliers within our groups, because we know these extreme values are going to bias our calculations, bias our statistics, especially means, which get really yanked around by the presence of outliers. So again, normal distribution of sample data, nice, not absolutely necessary. Another way to think about normality is in terms of the sampling distribution for our test statistic. And here, the shape of the test statistic is really important. The F statistic, of course, doesn't actually have a normal distribution of values, but it has a regular distribution that can be based on the normal curve. And the idea is if we have data in our sample that is more or less normal, or at least doesn't have a lot of outliers, if our sample is large and if our group sizes are equal, that is the number of people in the control group, in the placebo group, in the whatever group are all the same, then we can feel pretty comfortable in assuming that our sampling distribution for our F statistic will be regular in shape, and we will not have a lot of bias in terms of our interpretation of those results. We won't be more liberal in terms of our testing or more conservative in terms of our testing than we'd otherwise like to be. Arguably, this is really more important than the sample data itself, but in any case, I like to approach this in terms of first looking at the data itself, looking for outlying values and trying to understand if they exist, why they exist, and then proceeding onwards from there. And if you can reduce or remove the influence of outliers, you usually have a lot less trouble with various assumptions, including, in this case, the assumption of normality. Let's say we want to take a look at this in SPSS though, and this is a bit of a review, I know, because you probably, hopefully, remember that there are different ways to look at normality, and some of them can be found in the handy Explore module. So if we go to Analyze, Descriptive Statistics, Explore, and we put in our factor list dose of Viagra, that's our dose, our predictor variable, and our outcome variable is libido. This will allow us to look at the distribution values within each level of the predictor variable. That's what happens when we put dose on our factor list. So once you've done that, click on plots, and within the plots menu, you will find things like stem and leaf plots, histograms. I think those are checked. They probably don't need to be. But you'll also find normality plots. And you can also find a spread and level test for Levines test. That's a test of homogeneity of variance, so I might as well ask for that as well. Hit continue, hit OK, and we'll get some output. Here is some of the output. We get some normality tests. So we can, I did this separately, we can look at libido in terms of the whole data set, not breaking it down into groups. That's if you didn't include dose in the factor, in the box for factor. And you can see that the data is not significantly different from normal under either the Kolmogorov-Smirnov or Severe-Wilks test. The second box there is when you run the same analysis, but now you include dose as a factor, and you can see that within each of these doses we get basically the same sort of results, suggesting to us that the test is not significant, the distribution is not significantly different from normal, which is pretty good. Remember, these tests tend to be rather underpowered, and they're probably not as useful as they really ideally should be. They give us a general sense that, yeah, the data is more or less normally distributed. Running these tests shouldn't substitute for carefully inspecting the data for outliers, but given that we're just running through some examples, this is a pretty good way to go. Also, we can think about normality in terms of model comparisons, that is, evaluating how well our model fits the data. And here what we're considering is the distribution of errors or residuals. Ideally, we'd like those distributions of residuals to be normal in shape and not significantly different across our different groups. So we'd like to see a kind of a similar spread of errors when predicting values for our placebo group as when predicting values for a low dose group as when predicting values for our high dose group. If we saw big differences either in those terms of those distributions or in terms of their variances, then we get the impression that our model maybe does a worse job at predicting the level of the outcome variable in the high dose group than it does in the low dose group. That would give us a sense of the bias in our model. So this is yet another way to think about normality. And it's one way we can also explore in SPSS. So what we're going to do here is either in the general linear model module or in the regression module, I chose the regression module, we're going to save some regression diagnostics. And there are obviously lots and lots of options in both of these modules. For the time being, I'm really focusing on just some unstandardized and standardized, and I guess I clicked here as well, studentized residuals. What I want to do is I want to get a sense of the errors that the model makes when predicting values for people cases within each of our different groups. So you can get the same type of stuff in the GLM module. I just like to use regression module, and so that's what I've done here. Once I've got those values saved into my data set, I'm just going to go ahead and run tests of normality using the Explore module on those values, on the unstandardized, standardized, and studentized residuals. Now, to be clear, they're all the same, so I don't need to do all three. I'm just doing all three right now to illustrate that you could do all three if you wanted to. So you can see they are all not significantly different from what we'd expect under a normal distribution. And we can also see here a QQ plot, which is a lot like a PP plot. If the little dots line up on the diagonal, that suggests that they are distributed in a manner that's consistent with a normal distribution. An important point to make here is that if our data is normally distributed, if the raw data, the data for the outcome variable is normally distributed within in our groups, it's more likely that the residuals will also be normally distributed. So again, if you want to think about this from front to back, the first step you might take is to look for outliers. The second step you might take is to explore the distribution of the raw data itself for the outcome variable. And then you might go on to look at what's arguably really more important in terms of the model, which is the distribution of residuals. And hopefully you see kind of a generally consistent picture across these different steps of inspection. While we're at it, we can look at homoscedasticity in terms of the residuals as well. Remember, what we want to do is examine the distribution of errors, and hopefully the errors are not more variable in one group than they are in another group. There's a test for this. I may have talked about this before. I think I did in Unit 2, but if I didn't, it's Levines test. I'm pretty sure I did. And it just happens to be the case that I think Levine's test is in a couple of different places in SPSS, but one place it's in the plots menu of the Explore module. Why? I just don't know. And I guess I mentioned this a few slides back, but you can see here in the plots menu of the Explore module, we've got our spread versus level with Levine's test. Just run that on untransformed data. Maybe you already did that the last time you worked through this module. Another place you could find Levine's test is in the ANOVA module and in the GLM module. So here's just an example in the ANOVA module. For one-way ANOVA, if you ask for options, you can see here there's a little box for Levine's test or homogeneity of variance test. There's something similar in the GLM module, I think. In fact, I know, I just don't, have it pictured here. Anyway, however you find it, you get some output, and here's some output for the Levine's test in Explore. Here's some output for the Levine's test from the ANOVA module. And the basic idea is the same. If the test is not significant, then the variances of, in this case, the errors, we're looking at the errors, are not different across the different groups. The variances of the residuals are not different across those different groups. If you think back to Unit 2, you may remember this image, and it's one that I tried to create to illustrate this idea that we ideally want the distribution of residuals to be comparable, to be both normal in shape and comparable in spread at different levels of prediction. So we don't want it to be the case that at a high end of prediction there's a huge spread of residuals, at a low end there's a very narrow spread, or vice versa. That basic idea applies as well with our with ANOVAs. We just need to sort of imagine discrete groups instead of a continuous predictor variable. So what we'd like it to be the case is that the spread of residuals in one group is about equal in spread as in another group, and also that these distributions of residuals are normal or at least symmetrical in shape. So that hopefully that helps you visualize a little bit the connection here. It's also worth noticing that the distribution of data itself is related to the distribution of residuals. If you have a lot of outliers in one of these groups, then the residuals are going to be all over the place, and they're going to be different from those of other groups that don't have outliers. When the data is normally distributed in each group, then the mean for that group is going to be the best prediction for that group, meaning the residuals are going to be evenly distributed around that best prediction. And if that's true for all your groups, then your groups are going to have similarly shaped and distributed residuals, which is a nice thing, and certainly is an assumption that we make when we do an ANOVA. So it's not just a nice thing, I guess it's an important thing. Okay, so here are just some few more points to finish up before we, to address before we finish up. Here's what we should do. We should collect and maintain, if at all possible, equal group sizes. We should collect large samples so that via the central limit theorem we'll get sampling distributions that are normal or technically at least regular in shape. We can transform the data so as to make it more regular in shape. I've talked about this a little bit in previous lectures, but I'm not a big fan of transforming data because I think it creates a problem sometimes for interpreting data, interpreting results. It's also worth noting that there are so-called robust tests, like real robust tests, which are designed to work in situations where we can't make the assumptions necessary for ANOVA. Like, for instance, if we have really different variances in our groups and we suspect that the variances of residuals are just going to be really different, or if we have really different sample sizes. SPSS offers some of these, but they're in a separate software package, at least the last time I checked. So I haven't actually had a lot of experience working with them myself. I've noticed that R, the statistical programming language, there are tons of packages people have written for robust tests. There are also some non-parametric tests, particularly the Kruskal-Wallis test, which is kind of like a non-parametric analog to ANOVA. I should probably do a supplemental lecture on non-parametric tests. But for the time being, just note that there are options that you could use if you were in a situation where, despite your best intentions and attempts, you can't, you have data that really just doesn't allow you to comfortably make the assumptions that you want to make in order to do an ANOVA. So let's pause again, think about what we've covered. And again, if you're in my class, I'll ask you to write down a note to me for something that you understand, something that you don't understand. If you're not in my class, just think about this stuff. Maybe post a comment on YouTube. I'll do my best to find those and comment and respond to those. Anyway, here's a preview for next time. I'm going to talk a little bit about post hoc tests, trend analysis, and effect sizes. And we're going to get even more practice with ANOVA. Hooray! Thanks for being so patient. We're clocking in at just over an hour, so it's pretty typical for these lectures. I know that's a long time to listen to me talk. I hope I do so in a way that's engaging and at least somewhat entertaining for you guys. Again, if you have questions, please let me know. As always, thanks for your attention. Bye-bye.